Hi, welcome back. In this video, we're going to talk about how do we graph a rational function, but specifically focusing on vertical asymptotes. Now, we're going to be talking about in the following videos about different attributes of a rational function, like finding the horizontal asymptotes. Here are a couple of things we're going to talk about. Horizontal asymptotes. X and Y intercepts. Right? How do we find the domain? Poles. There are different attributes of a rational function that create a rational function that are part of it. And in this video, we're going to specifically focus on vertical asymptotes, what they are, how to find them, and I'll go through about 3 examples of it, okay? So feel free to press pause whenever you need to, take down some notes, do some examples with me, and let's begin. Now, while we're focusing on vertical asymptotes, one thing I want to add is that I will not be graphing these components at all for this particular topic, right? I'll be making a video for each. At the end of the unit, I will go over an example where everything gets covered in one piece. So I'm going to specifically focus on just the topic for today, and everything else will be somewhat of a sketch, okay? So let's go through this. All right, so let's start with the parent function. How do we graph this parent function? And we're going to talk about the vertical asymptote, okay? Whenever you graph any function, you're going to want to plot some points. How do we do that? Well, let's literally plug in points in a table, right? If you select a series of inputs and outputs, you'll be able to put them into the function, and you'll see where to plot it in the graph. So let's start with like some negatives and some positives, right? -3, -2, -1, 0, 1, 2, 3. We'll plot in a few points. And then my goal is to plug them into this equation, get an output, and graph to see what it looks like. If I plug -3 in here, I get 1 divided by -3, right? Which is approximately -0.333. So it's about down here. Right? If I go to -2, I get -1/2, which is -0.5. If I go to -1, 1 divided by -1 is -1. Right? Notice how the points are slowly going downward. If I plug in 0, 1 divided by 0, this is actually undefined. This value does not exist. We are not allowed to divide by 0. So what do we do here instead when we're dividing by 0? Anytime that happens, we're going to draw a vertical asymptote at 0. So x equals 0 is our vertical asymptote. Now, I'll go about explaining what this word means in a little bit. All we know is that at this part of the graph does not exist. It's ungraphable. Let's plug in more points. 1 divided by 1 is equal to 1. 1 divided by +2 is 1/2, which is 0.5. 1 divided by 3 is 1/3, which is 0.333. Notice how it looks very similar to this part of the graph. Now, what happens here, like if I keep going with 4 and 5, the fraction just keeps getting smaller, right? I'll just keep getting points lower and lower, something like that. What happens as I get closer to 0? Let's say that I go to 1/2. What happens if I plug numbers between 0 and 1? Here, right? If I plug in, like, say, 1/2, 1 divided by 1/2 is the same thing as saying 1 times 2/1, right? When you're dividing a fraction, it's keep, change, flip. And 1 times 2 is equal to 2. So at half, I go to 2. What happens when I plug in 1/3? Well, 1 divided by 1/3 turns into 1 times 3/1, right? Keep, change to multiplication, and flip the fraction. That turns into 3. So notice that as I put more numbers in here, more like closer and closer to 0, these decimals, these fractions would then turn into higher and higher values. And that's what ends up happening here, right? All of these points, as I get closer and closer and closer, they're just going to get closer to the line. But they will never actually reach 0. Same thing on the other side. The graph will look something like this. It'll just be sort of reflected on the other side, but on the negatives. Why is there a bit of a gap here? Well, no matter what I plug in, let's say that I plug in a really small number, right? Like let's say you get 1 over 1 and 1,000th. This is just going to go into 1 times 1,000 over 1, which is way, way, way up here, right? There's no value that I can plug in closest to 0 that'll ever touch this line. This is what we mean by a vertical asymptote. A vertical asymptote is this imaginary line. It's like a boundary, right? We can think of this as a boundary. An imaginary line that the function will get really, really close to, but will never touch. Because at that particular place, we start to divide by 0, and we cannot divide any number by 0. And we create this vertical asymptote. Now, some functions have 2 vertical asymptotes or more, right? But a vertical asymptote occurs when you have a rational function when you're trying to divide by 0, right? Now, a rational number by definition is any number expressed as a fraction as long as b is not equal to 0. I can write 1/2, I can write 3/4, I can write 7/10, I can write any number I want. I can even have negatives, right? 1 over -5. I can put all kinds of numbers. As long as this is not equal to 0, the number will exist. Well, here, plugging in 0 creates a value that does not exist. Hence, the vertical asymptote. All right, let's do another example so you can see what these kind of look like. So now here we have a little bit more complex situation, right? Anytime that you have a rational function, our goal is to first simplify the function as much as possible. Our goal is to work with the simplest form of the function. In the previous one, because it was just 1 over x, I didn't have to do any simplifying. Here, I can factor out a 2 out of everything in the top, right? This can just turn into 2 times. If I divide everything by 2, that turns into x squared plus 5x plus 6. And in the denominator, I get x squared plus 3x plus 2. Now my goal is to factor the numerator and the denominator, right? Feel free to use the columns if you need them, right? X times x gives me x squared, and 3 times 2 gives me 6. And at the same time, they cross multiply to 2x and 3x, so that adds up to 5, right? My factors are x plus 3, x plus 2. There's an entire video where I talk about how to factor, right? But our goal is to get comfortable factoring in this unit. In the denominator, now I want to factor x squared plus 3x plus 2. And you can do it over here as well. And then it's going to be 2 times 1. That cross multiplies and adds up to 3x. So now I have x plus 2, x plus 1. Notice how here I'm able to simplify the function. I can cancel some of them out. And now I have f of x equals 2 times x plus 3 divided by x plus 1. This is what I want to be able to graph, right? Now the function will have a vertical asymptote anywhere that you try to divide by 0. That's when this happens. Anytime you try to divide by 0, you're going to get an imaginary boundary, an imaginary line, right? So I start by looking at the denominator. I set the denominator equal to 0. And I can find out exactly what number the graph will create an asymptote. I know that there's going to be an imaginary line when this part is equal to 0. So at -1, I'm going to have an imaginary line. This is my vertical asymptote at x equals -1. Yeah. Now I can look at the points around it and graph points around it. Right? I can now plug in, I know that -1 is not going to create a value, so I can put undefined here. Here's my dotted line, right? And I can plot points around that. I'm going to plot points like -2, -3, -4. I can plot points like 0, 1, and 2. And my goal is to now use my new function, my simplified function, to plug in all of these points in there. Right? I can plug in 0 in here. I can do, let's see, 2 times 0 plus 3 divided by 0 plus 1. Right? I'm just plugging in for the x's. 0 plus 3 is 3. 2 times 3 is 6 divided by 1 is 6. So at 0 I go to 6. When I plug in 1 in there, I do similar. 2 times 1 plus 3 divided by 1 plus 1. This is going to give me 4 times 2 is 8 divided by 2, which gives me 4. When I plug in 2, similar. 2 times 2 plus 3 divided by 2 plus 2. Right, with PEMDAS, I always do parentheses first. This is 5 times 2 is 10 divided by 4. That's going to give me, what is that, 2.5? So when I plug in 2, I get 2.5. And you can sort of see the trend here, right? These points are going to slowly go downward, getting really close to the asymptote. And then over here, it'll just keep dropping this way. And then if I plug in these points as well into this problem, right, I'm going to get with like -0.6667. I'll get 0, -2. And you can sort of see the trend here. Is that negative? Well, it's positive 0.667. And then this will connect, but in the opposite direction, going closer and closer to this asymptote, but never reaching it. And then it'll flatten out over here. Something like this, right? The key thing here is that we're looking at the asymptote that the function will never touch. And I'm only focusing on the vertical asymptotes. I'm not going to focus on like x, y-intercepts, none of the other things. We'll focus on those videos later. For now, can you identify where the function will not exist? And that's always going to be by setting the denominator equal to 0 and solving for x. That's what creates the vertical asymptotes. Yeah. Let's try another example. The goal here is just variation, right? Can we get exposed to different examples, different scenarios, so that we can start to recognize how vertical asymptotes show up? Now here, there's nothing to simplify. There's nothing to factor on top. I could factor the bottom, right? If I factor the denominator, this is what I get. X times x, and then 4 times 1, and -4 specifically. The factors here turn into 1 divided by x minus 4, x plus 1. Notice how by factoring it, I'm not able to cancel anything on the top. So there's no simplifying for this one. We were able to simplify this previous problem, right? We factored the top, we factored the bottom, we were able to cancel the x plus 2's. And then we were able to get a simpler function. Here, even when I factor it, there's nothing to simplify. And that's okay, sometimes that happens. My goal is always to try to simplify if possible. Now, where will my asymptotes occur? Vertical asymptotes happen when I try to divide by 0. So, you set the denominator equal to 0. 0 equals x minus 4, x plus 1. Now, I've already factored it. You can set that equal to 0 or that, right? They're the same thing. If you don't factor it in the beginning, you would have just had 0 equals x squared minus 3x minus 4. The goal is to set the denominator equal to 0 and solve for x. Those are really the only the steps. So I would want to first simplify the function. Second, I would want to set denominator equal to 0, and my last step would be solve for x. That's really what I'm doing. I didn't have to simplify. I set the denominator equal to 0, now I can solve. I can solve these two separately, right? X minus 4 equals 0, and x plus 1 equals 0. By solving, now I have two asymptotes. I have two vertical asymptotes. At -1, I have an imaginary line. And at +4, I have an imaginary line. Right? I'm able to find the two places in the graph so that when I plug it in here, I get 1 divided by 0 as a whole. And that happens at these two places. Now that I know my asymptotes, I can make a table and I can graph points around it. I'm going to choose a few points. Like I'm going to first go to -1. I know that this is undefined, so nothing's going to happen here. And I know that at 4, I also have an undefined value. So there's an asymptote there. Now choose points around it. Choose points like -2, -3, -4. Choose points like 0, 1, 2, 3, and then choose numbers like 5, 6, and 7. I'm going to graph something on the left, something in the middle, and something on the right. That's really what I'm looking for. So I choose enough points so that I can see what the trend says and what it shows me. Now, for all intents and purposes, I'm going to just go ahead and give you a sketch, but you're going to want to plug numbers like 0 in here. 0 minus 3 times 0 minus 4, you're going to get a point. You're going to get some number, right? The sketch will look like this. It'll have like something like this on the left. It'll get really close to the asymptote that we found. Here, it's going to go really close on the bottom, close to the line, but not really touch it. And then over here, it's going to be close to this line and also not touch it. And then on the other side, it'll get really close to that line and not touch it either. This is just a sketch, right? But the goal is to show that the asymptote creates a boundary, right? An imaginary line that the function is going to try to get really close to and never touch. On the top and in the bottom, and in the bottom and in the top. We'll focus later on horizontal asymptotes and all that stuff. For today, we want to identify a vertical asymptote. So, follow these 3 steps. Simplify the function whenever you can. Set the denominator equal to 0, like we did here. And then solve for x. That gives you the vertical asymptotes. That's what's going to create that imaginary boundary that the function will get really, really close to but never touch. I hope this has helped. Please let me know if you have any questions. Don't forget to like and subscribe, and I'll calculate.